Starting from rest at a stop sign, a 1,500 kilogram car accelerates over a distance of 50 meters up to a speed of 17 meters per second. And at that point, the driver coasts up an 8-meter high circular hill that has a radius of 20 meters. Air resistance and friction are negligible, which indicates that we're probably going to be using conservation of energy for parts of this problem as opposed to the work energy theorem. Part A, calculate the acceleration of the car during the first 50 meters. So this is going all the way back to just basic kinematics. We know the initial velocity of the car is 0 since it started at rest. The delta x, the distance the car moved, was 50 meters. The final velocity of the car was 17 meters per second. And we're trying to find the acceleration. So since time is missing, we're going to use the last kinematics equation. V squared equals VO squared plus 2A delta x. And we know that VO was 0, so we can get rid of that term. Rearrange the equation for A. Remember, always rearrange first before you plug in the numbers. And you get V squared over 2 delta x. And 17 squared over 2 times 50, 289 over 100 gives you the 2.89 meters per second squared. For part B, calculate the speed of the car at the top of the hill. Well, now because we're dealing with a curved path, we can't use kinematics anymore since the acceleration is not constant, but we can just use conservation of energy. So we can say that Ki plus Ui equals K final plus U final. The initial variables refer to the car when it's at the bottom of the hill, and the final variables refer to the car at the top of the hill. And at the bottom of the hill, because it has no height, we can say the initial potential energy is 0. But it is moving at the bottom of the hill, it's moving at the top of the hill, and it has gravitational potential energy at the top of the hill, so nothing else goes to 0. And then plugging in the formulas, we will have 1/2 mv initial squared is equal to 1/2 mv final squared plus mg h final. Notice that all three terms have a mass in it, which cancels out. And from this, you can just rearrange the equation to solve for the v final. So to get vf by itself, you want to first bring this term over to this side. Then you're going to multiply by 2 to get rid of the 1/2, and then have the square root. So we start off with 1/2 vi squared minus g h final is equal to 1/2 v final squared. Multiplying everything by 2 would get rid of this 1/2, get rid of this 1/2, and it would have put a 2 in front of that term. And then with the square root, you end up getting Vf is equal to the square root of Vi squared minus 2g h final. Plugging in all the numbers, you have 17 squared minus 2 times 10 times 8. That's 289 minus 160. So you get the square root of 129, which is approximately equal to 11.36 meters per second. And it's good when solving these problems to, right before you get to the final answer, if there's a square root on there, just write the square root of whatever the number is, because since kinetic energy depends on v squared, oftentimes when you take a square root, and then in a later step, you're going to have to then go back and square it. So it's easier to square something like this, because when you square a square root, you just get rid of the square root sign. It's easier to do that than it is to square something like this and round up. So, and you'll see what I mean as we get to this next part, because another thing that depends on the square of the velocity, other than kinetic energy, is centripetal acceleration. And in part C, the question says, calculate the acceleration of the car at the top of the hill. At the very top of the hill, the car has stopped slowing down, because as the car was coasting up the hill, it's slowing down, and then as it coasts down the hill, it speeds up. So the top of the hill is the only point where it's actually not accelerating, at least horizontally, but because it's going around a circle, kind of like on the outside of a circle, if you look at the overall shape of the hill, as the cars move around the hill, when it gets to the very top of the hill, because this forms a circle, technically the car has centripetal acceleration directed toward the center of the circle. So at the very top of the hill, we want to solve for the centripetal acceleration, which depends on the v squared. And since v was equal to the square root of 129, that means v squared will just be equal to 129 without the square root, divided by r, the radius of the hill, which was 20 meters, and that gives you 6.45 meters per second squared. So it is a centripetal acceleration that the car has when it's at the top of the hill. Let's erase this to give us more room. And then in part D, we want to draw a free body diagram. So the free body diagram for the car, when it's at the top of the hill, it has a gravitational force acting on it. It has a normal force acting on it, and that's it. And if you want, you can include the squiggly arrow representing the direction of that centripetal acceleration. Now notice one of the main differences here between this and some other problems we've solved is that if you have a car that goes through a loop like this, or an object that goes through a loop, if it had, the car or object has to have a high enough speed to be able to make it through this loop. And if it's going too slow, it's going to lose contact with the track. Whereas in this problem, since the car is technically going on the outside of a circle, the car has to go at a slow speed to avoid losing contact with the track, so we can just go over. If it goes too fast, it's going to just kind of go flying off and lose contact. So with this one, we want to find, in part E, the minimum speed the car must have at the top of the hill for it to momentarily lose contact with the road, because anything greater than that is definitely going to lose contact with the road if it's going too fast. So to lose contact with the road, remember what happens is that means the normal force has gone to zero. So let's set up Newton's second law for this, which is net force in the y direction. Make that look like a y and not a g. Net force in the y direction is equal to the mass times the acceleration. Since the acceleration is downward, I'm going to make downward the positive direction. So that'll be Fg minus Fn is equal to, and that should be a c subscript on there because it's centripetal acceleration we're looking at. And we just said to lose contact with the road, the normal force would go to zero. So we're left with the gravitational force, which is mg, is equal to m times the centripetal acceleration, which is v squared over r. Both terms have an m in it, so you can cancel those out and then rearrange the equation to get the v by itself. You multiply both sides by r and square rootify it. You get v is equal to the square root of r times g, which is equal to square root of 20 times 10 square root of 200, which is approximately equal to 14.14 meters per second. So at that speed, it would lose contact with the hill. And notice that the speed we got earlier, when we calculated for the actual speed at the top, is 11.36, which means at that speed it would not lose contact with the hill because it has to be going greater than the 14.14 meters per second. And finally, in part F, we want to calculate what acceleration the car must have had during the first 50 meters to achieve the speed that would give you 14.14 meters per second at the top of the hill. So this is going to be a two-part question, because first we have to calculate the speed at the bottom of the hill using conservation of energy. Ki plus ui equals kf plus uf. So if we look at the bottom of the hill for the initial position, the ui, the potential energy, is 0. And plugging in the formulas, we have 1/2 mv initial squared is equal to 1/2 mv final squared plus mgh final. All terms have an m in it, so those will cancel out. And you want to solve this equation for the v initial, which is the speed at the bottom of the hill. Multiplying every term by 2 would give you vf squared plus 2gh final, and then you also have to get the square root of that. Plugging in all these numbers, you get v final squared, which is, if you look back over here, the final is the speed at the top of the hill, so the v final was square root of 200, so the square root of 200 squared is just 200 plus 2 times 10 times 8, which is 160. 200 plus 160, that gives you the square root of 360, which is approximately equal to 18.97 meters per second. So that's the speed that is needed at the bottom of the hill. And then we want to solve for the acceleration needed to bring you up to this speed, which is going to be exactly the same thing we did way up here. Because you knew the initial speed is 0, the distance is still 50, the v is now going to be the new value, which is 18.97, or we can just say the square root of 360, and the acceleration is what we're looking for. And then when you plug it in to this equation, the v squared will just be the 360. So you have 360 divided by the 2 times the 50, or 100. 360 divided by 100 gives you a final answer of 3.6 meters per second.